Dear students, so in this video we are going to discuss about how to develop the expressions for the deflection, that is vertical deflection, and bending moment at the midspan of a simply supported beam which is loaded with UDL throughout its span using Rayleigh-Ritz approach by considering the trial function as polynomial function. Okay, so the total length of the simply supported beam can be considered as L meter, and the magnitude of the UDL subjected on the beam, considered beam, can be taken as generally W Newton per meter. So we all know that the governing differential equation for a beam element is EI d power 4 y by dx power 4 minus W is equal to 0, which is described between the limits 0 to L. Okay, and the essential boundary conditions we can observe from the diagrammatic representation of beam. At x is equal to 0, a constraint is provided, and at x is equal to L, a hinged support is provided. So there will be no vertical deformation. So at x is equal to 0 and at x is equal to L, there will be no deformation. So these are the essential boundary condition. So vertical deformation at x is equal to 0 is 0, and the vertical deformation at x is equal to L is equal to 0. Okay. So in the problem it is asked to consider the trial function as polynomial function. So we can assume a trial function generally as y of x is equal to a0 plus a1x plus a2x square. Okay, so to follow the Rayleigh-Ritz approach for solving structural problems, the main point to be noted to be we have to use only essential boundary conditions while simplifying to frame the trial function. We need not go with the natural boundary conditions. So only I have taken these two boundary conditions to finalize the trial function. Okay, so now we can apply the first boundary condition in equation 1. So at x is equal to 0, y is equal to 0. Okay, so y of 0 is equal to a0 plus a1 into 0 plus a2 into 0 square is equal to 0. So a0 is equal to 0. Okay, so then apply the second boundary condition in equation 1. So y of L is equal to a0 value already in the previous step has been calculated as 0 plus a1 into L plus a2 into L square is equal to 0. Okay, so a1 L plus a2 L square is equal to 0. So that gives a1 L is equal to minus a2 L square. a1 is equal to minus a2 L. So by applying the two boundary conditions described in the given problem, we have calculated the values of a0 and a1. Okay, so now we can substitute the values of a0 and a1 in equation 1. So y of x will be a0 is 0 plus a1x, a1 is minus a2l into x plus a2x square. Okay, so simply we can write this as a2 into x square minus lx. This is our trial function. which satisfies the given boundary conditions. Okay. So to solve this problem using Rayleigh-Ritz approach, we can use this relation, that is potential energy pi is equal to strain energy U minus work done H. So for beam problems, the strain energy formula is known to be EI divided by 2 integral 0 to L d squared y by dx square the whole square dx. Okay. So here EI values are constant for a particular specific problem. Here we have considered the deformation function as a2 into x square minus lx as a trial function. So now we have to raise this equation 2 to the order of 2 to substitute here d square y by dx square. So now to apply the values in equation 3, we have to differentiate equation 2 with respect to x twice. Okay. So dy by dx is equal to equation 2 we differentiate panna porom with respect to x. So a2 into x square differentiation 2x minus lx differentiation L. Then d square y by dx square, again we have to differentiate the above expression with respect to x. So a2 into 2 minus 0, so 2a2. So now we can substitute the d square y by dx square value in equation 3. So u will be EI divided by 2 integral 0 to L d square y by dx square value is 2a2 the whole square dx. So EI divided by 2 integral 0 to L 4a2 square dx. So we can take out these constant value outside the integral. So EI into 4a2 square divided by 2 integral 0 to L dx. So 2EI a2 square, integral value is x between the limits 0 to L. So 2EI a2 square L. So this is the strain energy value for the given problem. So equation number 4. Then work done H formula is known to be integral 0 to L W y dx. Okay. So integral 0 to L W into y value as the trial function a2 x square minus lx dx. So constant values WA2 integral 0 to L x square minus lx dx. Now we can integrate x square minus lx with respect to x. So x cube by 3 minus L x square by 2 integral limits 0 to L. Now we can apply the limits. First upper limit L cube by 3 minus L into L square L cube by 2 minus lower limit apply பண்ணும்போது all the values will be 0. While taking LCM 2 L cube by 6 minus 3 L cube by 6. So 2 minus 3 minus 1, so minus L cube by 6. So minus WA2 L cube by 6 is the work done value. So now potential energy pi is equal to U minus H. So U is 2EI A2 square L minus h is minus WA2 L cube by 6. Minus. Okay, so simply 2EI A2 square L plus WA2 L cube by 6. So to find the value of A2, now we can apply the principle of minimum potential energy, that is dou pi by dou A2 will be 0 for the equilibrium condition. Okay, so dou pi by dou A2 will be 2EI A2 square 2A2 into L plus W into the differentiation for A2 as 1 L cube by 6 is equal to 0. Okay, so 2 into 2 4EI A2 L is equal to minus W L cube by 6. So A2 as minus W L cube by 6 into 1 by 4EI L. So A2 is minus WL square divided by 24EI. Okay, so now we can substitute the value of A2 in equation 2. So y of x is equal to A2 is minus WL square divided by 24EI into x square minus LX, or WL square by 24EI into LX minus x square. So this is the expression for the deflection experienced by the beam, cantilever beam, simply supported beam, when it is subjected to UDL throughout its span. Okay, so this is equation number 5. But in the problem it is asked to find out the deformation at the midspan. So at the midspan x is equal to L by 2. So at x is equal to L by 2, y is WL square divided by 24EI into L into L by 2 minus L by 2 the whole square. So this is L square by 2 minus L square by 4. So the resultant is L square by 4. So WL square divided by 24EI into L square by 4 as WL power 4 divided by 24 into 4, 96EI. So 1 by 96 is 1 divided by 96 is 0.0104 WL power 4 by EI. So we know the standard formula for this case, that is, when a simply supported beam is subjected to UDL, the maximum deformation will be experienced at the midspan, and the value is y max is equal to 5 by 384 WL power 4 by EI, which is also 0.01 WL power 4 by EI. So next, bending moment. We know the expression for bending moment, M is equal to EI d square y by dx square. So already for the assumed trial function we have calculated the value of d square y by dx square as 2a2. We have calculated the value of a2 as minus WL square divided by 24 EI. So we can cancel these two terms. 2, 12. So minus WL square divided by 12. So the actual formula for this case is minus WL square divided by 8.